Hi everyone, I'm going to do an example for you here just using the iPad and writing on the screen. So let's go ahead and finish the very last slide that you would see on the lecture slides that I posted to Piazza yesterday. So here I have an example of flexural buckling with column bracing here, and this sort of gets to what I was talking about with the building frame and how the columns are oriented in the structure. So this really kind of ties together the beginning of last lecture and the end of this lecture slide set, this PowerPoint set. So here I've got a column, it's A992, so I know Fy is 50 KSI. Right, that's what I want to know there. I have my shape, and the shape tells me, right, these, I drew an arrow there, but the shape tells me these things, right? The shape tells me the area gross, the radius of gyration about the x, and the radius of gyration about the y. And especially in this example, I need to know both rx and ry, because as you can see here in the figure, I have kind of a complicated set of different bracing applied to this column, and then potentially I could have different boundary conditions. But for right now, let's just start this off and say that this point here is a pin, and then you see down here it says assume assume the bottom as a pin. So I'm also going to have a pin here, so I'm just going to draw a little pin like that. Excuse me. So now I've identified the kind of top and bottom of the overall column, and if I were to draw that like I did in class, I would say this is the x-axis. Sorry, yeah, this is fine. X-axis, and then maybe y-axis, and I'm probably gonna erase this later, but just so that you can see the similarity. So I drew something like this, and I said this is one column. This is what I said in class. Both of these little stick figures that I just drew represent one column, and so what I'm drawing right here is going to be very similar to what you see on your homework. I believe it's problem 3, and I've only drawn one figure, but I've combined them by showing a bracing point like this. And I say pretty explicitly in the homework that some bracing applies only to the x-axis or the y-axis, etc. But here I'll draw two figures and then I'll combine them into one to represent this column in the same way so that you can see the similarities. Okay, so we've got this column. You see this bracing here, and this bracing here, and this bracing here, and this bracing here. So the top is braced, and that's why, right? That's why I can call this a pinned support at the top. And I'm calling it a pin support at the top, and you can see both x and y axes I've called pin support. So this is physically representative, right? Kind of a better drawing representation of these both axes being pinned. This is not exactly what we would see in a building. We don't use flat plates like this. These would be other floor beam members or something like that would frame into the column. And that's what I was talking about in class. So then that takes care of this point, right? So we're good at the top. At the bottom, well, it's the ground. You can kind of see that it's the ground. And we've said that that's a pin, so here, x and y axes, I have pin. There's no difference between supports in x and y axes. But let's turn our attention to this middle piece here, this middle connection. So this middle connection, what I would draw in these figures on the right here, it's only bracing the y-axis, and I think you can see that physically, right? If it were to buckle about the x-axis, so I'm going to draw kind of just a hypothetical buckle about the x-axis like this, these, let's see which color do I want to use. We'll call these braces as yellow, right? These braces would go with it. So they would remain. with the attached to the section. So I hope that clears that up a little bit. All right, so it's only bracing the y-axis. So in the figures on the right, I would see only this brace. I would see this brace here, only applied to the y-axis. And in the way I've shown in the homework, I wrote bracing applies to the y-axis, or I think I said bracing y-axis only. This is what I said on the homework. Okay, so let's block this one off for now, and let's turn our attention to the x-axis. The x-axis, I'm going to erase this. Whoops, I don't want to erase all that. I want to erase this. So now the x-axis, I just drew the buckled shape. Well, why did I draw it the full the full length, right, from very top to very bottom? Why did I draw it buckled like that? Well, look along the x-axis of the column. There's no bracing. I would need bracing like this, somewhere along the x-axis. Or sorry, somewhere along the length in order to brace the x-axis. This one at the top, these two red lines, those indeed are bracing the x-axis, and we see it right here at the top. Okay, good. So I didn't draw anything in here, right? This doesn't exist. There's nothing there. So the x-axis picture is correctly represented as drawn. There's no bracing. Okay, so now I think we can combine these two, and the way I'm going to combine it is literally just erase this and that, and now you have exactly the same type of picture that you've got in your homework, but there's only one unbraced length, or sorry, there's only one bracing point for that y-axis. Okay, so now we're very similar to the y-axis, and you can see physically what it looks like here. Okay, so let's fill in some information. The y-axis here, this is 20 feet. Well, that's shown right there in 20 feet. And this is 25 feet. Good. That gives me two different lengths that I need to check for my y-axis. All right, that gives me two different lengths. One length is 20 and one length is 25. Okay. So let's draw just a couple more things, and then we'll get into the meat of how to actually carry out the equations. Okay, so now we have this picture here, and this picture here is physically representing that. Let's draw the x-axis buckling. So let's talk about only x first. So I just said there's two lengths for the y, but there's only one length to check for the x. I don't really like my shape there, so I'm going to draw it again, or something like that. Right, so this is the x-axis. So for x-axis, I'm going to say LC over RX. And I'm going to put an x here too, just to really drive home the point that there's a different unbraced length for the x. LC I know is K, LX over RX, that's good. Now for K, I know it's pinned, right? Because for the x-axis, I'm going to put X here, is pin. I'm just going to say pinned both. That means 1, right? So I have 1. And then my L, right, the effective length is this full length. It's the 45 feet. So I have 45 feet. And I'm going to divide by R, and as you can see over here, RX is in inches, so I'm going to change this to inches per foot, and I have 5.65 inches. Move this over a little bit, okay. And I get a ratio, or sorry, I get a ratio. This slenderness ratio. Right, this is the x-axis only. Fix my writing here. Slenderness is 96.5. Now there's no units, right? It was inches per inch. That's crossed out, so no units. It's just a ratio. It's a slenderness ratio. What do I need to do with that? Well, my goal here is to find the nominal axial compressive strength. That's the same thing you're trying to do in your homework. So I'm going to go in to chapter E3, and I'm going to compare my KL over R, or actually I should say it's my LC over R. This is new for this edition, so it's kind of something I'll forget and say two different ways sometimes, but I have this one for my x-axis, and I want to compare it to, right, 4.71 square root Young's modulus over Fy, and I have 4.71. Well, I'm just going to write it out down here. Young's modulus is 29,000. Remember we said that we know that one, and we have Fy is 50 KSI. So if I carry that out, I get about 113. I'm not going to worry about decimal points at this point. And I wrote these numbers down, but you should know them by now. I'm going to erase them to give myself some space. So yeah, this is true. So this is verified, right? This is indeed the case. So that means I use E3.1 part A, and that is F critical equals 0.657 Fy over Fe times Fy. My Fe is Euler, right? This is the Euler buckling stress, pi squared Young's modulus over KL over R squared. Now, it's very important. This KL over R is whichever KL over R I used here. And whatever KL over R I used here is the one that I used here, right? So I got to keep them straight. So I'm only looking at the x-axis. That means right now I'm considering the x-axis. So I need to use the x-axis values. Right, but if I keep it all in line like this, it's pretty easy to keep straight. So I've got 29,000 KSI, Gibbs per inch square, divide by 95. It's kind of convenient because I already have that number, right? I have that number right there, so I can just plug it in. And I should get, what do I get? It is 27.5, and I ran out of room. Let me scoot it over here a little bit. Scoot that over. We'll scoot this over too. There we go. And we'll go this one. Now we have KSI. Okay, so this is the Euler buckling stress. If we didn't consider material nonlinearity, and if we didn't consider, out of straightness and all these things, we would assume that the column would buckle at this stress, just using Euler formulation. But we know better than that. We are using the AISC specification after all, so we're going to follow the guideline because we have satisfied this requirement that puts us in the inelastic flexural buckling zone. So I'm going to plug in up here, or down here rather. I have 50 KSI divided by 27.5 and 50 KSI. And I end up with 25.6. Now right in this in this example, right, there's not too much difference between these two. But as you get but the thing to pay attention to is these two are pretty close. So what does that mean in terms of this plot that you're going to get really sick of seeing? Right? Here's the 4.71 square root E over Fy. This is 113, but we're 90 something, 95. So we're really close. So the difference between these two equations, this is the Euler part, right? Or I should say it's this one. Fe, and this is the one that we just used, right? There's not too much difference in this zone, so it's not too surprising. I'm going to get rid of all this stuff. That's just to tie the two pieces together. But knowing things like that, are really good because for your practice, because you don't want to just blindly plug and chug. If you you may see this and then start to freak out. Oh man, did I do something wrong? Well, you understand the concepts, and so you're okay with this result. And that also can help you, you know, in your computer, checking computer analyses and all that. Okay, so are we done? Well, no, because we want the nominal axial compressive strength. That means I need to say, what's the nominal, right, axial? It's F critical times AG. So the gross area, right, we're not doing tension now. We don't have any bolt holes. We're not considering rupture or anything like that. That plot that I just erased, like this, right, it doesn't even barely go up to Fy. So we're definitely on the gross cross-section. This is a ductile type of failure, right? So we're in inelastic flexural buckling. That stress applies to the whole cross-sectional area. That's what I'm getting at. So here's my nominal. I have 25.6 KSI, and then here's my area from before. It's 44.7 inch square. So my nominal is somewhere over here. Let me look at my paper. Nominal is, where did I write it? Sorry, looking for it on my page here. And there's my phone. 25.6 times 44.7. Boy, you probably could have done that a lot faster than I did. It's 1144.3 kip. Good. But what does it mean? It means at 1144 kip, we get the blue buckled shape here. This is about the x-axis. We haven't even considered the y-axis, so let's look at the y. What's the y going to do? Well, the y starts, right now, notice I'm being pretty deliberate in how I'm drawing this. Whoops. Deliberate and not very good. There we go. Right, it's in this plane, right, this type of a plane. That blue one is in the other plane. The blue is in this plane. So this is buckling about the y-axis. Now I have two different cases for the y. I need to consider length of 20 and length of 25. Well, since this is pin and this is pin, right, just like we see here, this length is pin, pin. This is what we're looking at here, this red curve. Oops, I wanted to get rid of that. Here's our red curve. Right, since this is pin and this is pin and this is also pin, all things are pretty much equal. So we know that the 25 is going to govern, right? So I'm going to retain this one. And I'm going to get rid of all this stuff, and we're going to do the same calculation with the y-axis. So let's just put that here. Put this here. I'm going to get rid of this, and let's just park that right there. Okay, so now let's do in red, y-axis. So I technically do have two lengths, right? I have LCY1 is 20 feet and LCY2 is 25 feet. K is 1 and K is 1. So I know this one's going to control, because I know the larger KL over R is always going to control. So my KL over R, Y is equal to 1 times 25 feet. Remember, I need to convert inches per foot. And, whoops, get rid of this. Over here on the right, my RY is 1.77 inch. That gives me a KL over R equal to 169.5. And that is not smaller than 4.71 square root E over Fy. If you remember, this was equal to 113. Therefore, I need to use E3.1b, right? So F critical is equal to 0.877 times F Euler. And we found out the F Euler from before. Oh, can we use that one? No, we can't use F Euler from before because we have a different K over R value. So don't fall into that trap. Pi squared, Young's modulus, over 169.5 square. All right, so every time, what I was saying there, don't fall into the trap. Every time we're considering a different case, even if it's the same column, we have different cases, right? I need to be consistent. I have K over R, I need to use K over R, I need to use K over R. So you got to keep everything straight. It might seem obvious or it might not. But now look what we get. 8.7 KSI. Whoa. Whoa, vastly different. Vastly different. Oh, I'm sorry, that incorporates the 0.877. Hold on, 8.7 divided by. This should be 9.9. Let's just double check. You can hear my calculator. Oops. Yep, 9.96 KSI. Now my F critical, remember this 0.877 accounts for out of straightness and slight eccentricity, accidental eccentricity, eccentricity load, right? Times my F Euler, and that equals 9. Well, let's do it in a nice clean way. 9.96. Now I get my F critical is 8.7. Looked a little bit too far ahead of my notes there. Okay, again, we're not done because this is the stress. We need nominal axial compressive strength. So we have strength, that's Pn, F critical times, times Ag. I have 8.74. Ag is 44. And I end up with, Pn should be 389. This is for y-axis. Okay, so now I had two cases that I considered, x-axis and y-axis, and very clearly the y-axis controls, right? Okay, so before I end the video, what we did, right, remember, we considered two lengths for the y-axis, these two lengths, and we only considered one length for the x, and that's because the x, the only bracing points or the only boundary conditions were at the very top and at the very bottom. But for y, we had a bracing point or a boundary condition, right, at the top, at the middle, or roughly the middle, and at the bottom. So we had two different y lengths, y1 and y2, that's here, right, and we needed to consider those. So I thought this was a nice example to show kind of like a sort of realistic version, and then also how does it look in kind of like a stick figure. Okay, hope it helps. Thanks.